So our next speaker is Eshita Eva from the Ohio State University.
Thank you, Mike. Um, Hello all, I'm Eshita Eva, PhD candidate at the Ohio State University. So today I'm going to talk about comparison of importance of ancillary variables for two different sources of daily soil moisture downscaling over the CONUS. So why downscaling? Why do we need downscaling of the soil moisture products? So a lot of us already discussed about why soil moisture is important. I want to add a little bit more. Soil moisture is a significant variable in the climate system. It is important to examine and assess the drought and the flash flooding. It also helps to predict the stream flow and other hydrological parameters like such as groundwater flow, base flow, and percolation, evapotranspiration. In terms of agricultural purposes, it helps to determine the irrigation scheduling, crop yield, disease outbreaks, and pest controls. While soil moisture is so important, national soil moisture products are not available with high resolution, um, such as satellite-derived products. SMAP is limited to 9 km, and then model-derived product NL-, which is limited to 12.5 km. Uh, for these products are not convenient for field scale application for agricultural purposes, and most of them are not products are not fast and easily accessible, and they are limited to ancillary variables. That's why my project, the goal of this project to address the critical need to enhance the utility of the daily national soil moisture products. The objective of this study is to compare the importance of these variables for two different sources, SMAP and NLS, and also two units of measurement, which is volumetric water content and percentile. And the novelty of this study is that most of the previous study was limited to using 4 to 5 ancillary variables, but in my study, I have used 14 different variables, and I have divided the CONUS into 9 different regions using the satellite and model both products and incorporate these 14 variables to downscale the soil moisture for volumetric water content and percentile. So this slide is representing the 6 variables out of 14. I have not added those 14 maps. And from the digital elevation model, I have calculated slope and aspect too. And I have calculated antecedent precipitation index from the precipitation. And I have also calculated daytime range temperature from subtraction of maximum temperature to minimum temperature. And also I have included dew point temperature. And from the vegetation aspect, I have included NDVI, normalized difference vegetation index, and LAI, leaf area index. And I use gridded GSARGO data sets for soil texture. So I have divided my whole workflow into two parts. So first part is all about model building. So once I have collected all the 14 input variables, I have done the aggregation. And for aggregation, I have used nearest neighbor interpolation. So using nearest neighbor interpolation, I have aggregated those variables to 9 km for SMAP downscaling and 12.5 km for NLS downscaling. Once I have those variables to 9 km and 12.5 km, I have applied random forest. So random forest is a robust algorithm. So it can handle high dimensional and nonlinear data sets and noisy data too. So those who are interested in random forest, I am not going to talk details about it. If you are interested, please talk to me later. And then I have, and also random forest has a unique feature that it can rank those ancillary variables according to the value. And that's how I get the feature importance of forest map 9 km and NLS 12.5 km. And the second part is model application. So if I want to downscale to 1 km, then I have to have those input variables of 1 km. So again, I use nearest neighbor interpolation. And then I collected almost 1,200 soil moisture in situ data sets to validate the model. And then I have this final downscale soil moisture 1 kilometer products. So the result shows pretty much similar for SMAP and NLS for both units of measurement. This figure is showing the for the CONUS SMAP volumetric water column 9 kilometer, and here is showing that elevation is the highest ranking variables, and it has the most influence on downscaling, and dew point temperature is the second highest, although maximum temperature also has some influence on that. And then I have divided the CONUS into 9 different regions. And here the difference is that dew point is the highest influence variable other than, but for South and West North Central region, elevation is the highest. But for South and West North Central regions, dew point is the second highest variable. And this is SMAP percentile 9 kilometer. So here is the figure is showing that dew point temperature is the highest, and then the API, antecedent precipitation index, and then the elevation. But we can see that the temperature variable like minimum, maximum, and DRT also has some considerable amount of influence. And the next one is, again, the dew point temperature is the highest for all the 9 regions except South region. For South region, elevation is the highest one. And this is NLS VWC 12.5 kilometers. So I'm not going through that again. The dew point is the highest variable, dew point is the highest variable. So, and the same elevation for South and Southeast region, elevation is the first one. And the NLS percentile of 9 kilometers, this is again it is showing a little bit different because API is the highest variable for Southeast and South regions, and West, North, Central, and South regions, again, the elevation has the highest influence on that. I have calculated RS square, MSE, MAE, RMSE, and UBRMSE, but I have not added all those accuracy matrices. So I have just included RS square, and in the next slide, I have included UBRMSE. And I'm not going to over the details about it because this is too much value. So all I am going to say that South region is showing the higher accuracy, and though this value is not good because model calculated the accuracy matrices for each day of those 1,200 stations. And then I did the average for whole years, like for SMAP, this is the average from 2015 to 2021. And for NLS, I have used like 2001, 2021. So that's why the value is a little bit lower. But I have done the analysis that if I just take one state, suppose Texas, the value is more than 0.8. And then the EV value. So the main takeaways of my research is that dew point is the influential variable. And in terms of BWC downscaling and percentile, BWC is showing the better accuracy, and NLS is showing more accurate than SMAP datasets. And my next step will be I'll consider other machine learning approaches like support vector machine, artificial neural network, and long short-term memory, and hopefully convolution neural network. And my present study is about downscaling 1 kilometer, but in the future, I will consider other resolution 2 kilometer, 700 meter, and 400 meter to check that which resolution is performing better. And my last but not the least, that I'll make these data available through a website so that everybody can have access to data sets. Thank you.
Questions for Eshita?
Where are you acquiring your soil input data set?
What soil data set are you using?
Yeah, soil texture, percentage of sand, silt, and clay.
Tyson's all the way in the back. You could sit next to me, Tyson.
Thank you. Really nice job. Thanks for sharing your work with us. I'm curious, two questions. Where are you getting the dew point temperatures, and why do you think that is showing up as an influential variable in your calculations?
So dew point temperature and other temperature variable precipitation, all these are from PRISM, parameter regression independent slope models. You know, that is, and the resolution is 4 kilometers. So then I have aggregated this to 9 kilometer and 12.5 kilometer. And why the dew point temperature? That is a very good question. So dew point temperature has the influence on like the vegetation and all, like the surface soil moisture, because I am dealing with the 5 centimeter surface soil moisture. So because of the temperature and the precipitation, so dew point temperature is going to affect on the soil moisture, surface soil moisture basically.
There are no other questions. We'll move on. Thank you, Eshita.